Glaciers are formed by snow that accumulates over thousands of years. As the snow compacts into ice, the glacier increases in size and becomes incredibly heavy. All that weight pushes the glacier down and forward. Even though it's made of solid ice, a glacier moves and flows much like a river, carving out sediment as it goes. I'm Science Mom.
And I'm Math Dad.
Join us today to learn about the dynamic and fascinating world of glaciers. Hello to Denali from California. I see Eric from Pennsylvania, Claire from California as well.
I'm excited to learn about glaciers. I don't know a lot about glaciers.
Me?
Oh, did we get Alicia from Nevada?
Yes.
Oh, yeah.
And I want to give a special welcome to anyone who's watching the replay and say that to learn about glaciers, it helps to talk just a little bit about ice first. So I have an ice cube here. Why is this not a glacier, Math Dad?
Okay. I've got a theory. If it's man-made, it's not a glacier?
Well, let's sit it right here and see what happens. I've got it on a slope, but is it moving?
No. So a glacier has to be moving.
A glacier has to move under its own weight. And if I get a bigger piece of ice on this slope, watch what happens. I'm going to need you to push down right there so that our cookie sheet stays sloped.
What are you doing, Science Mom?
I have a big block of ice.
Oh my goodness.
And if I set this one on, is it moving?
Well, actually, yes, it is slightly moving.
Slowly. It is.
Oh my goodness.
Slowly going and creeping down our slope.
Okay, so that one's a glacier.
Well, in the natural world, this is going to melt and before it can get too far, right?
Yeah, it's a pretty smooth slope there as well.
And yeah, in the natural world, we're not going to find a slope quite this flat and smooth. But you can see that this one is slowly moving down the slope, whereas our small ice cube, as soon as, here, I'm going to give this one just the smallest nudge to the side so that you guys can see. Well, never mind.
Okay, that was big nudge.
That was a big nudge. Our small one is not moving. It's still up here because the slope is not very steep. It does not have enough weight to go down the slope, but this big block does.
I bet if we give it a few minutes, maybe it even will move, but we'll see. That's my challenge.
So this is the thing that really defines glaciers. They move under their own weight. And when we say move, they're going to be moving slightly downhill. So you get glaciers.
So it's just gravity that's pulling them?
Gravity is making them move downhill, and all that pressure of their weight can actually form melted water underneath. And that kind of acts like lubricant, sort of lubricates the bottom so that then they can slide forward.
Like ice skating works under the same principle, right? Water's melting and it's giving you a little,
it's making it easier to slide. There's less friction. Now, what if I had filled up this tray with potato chips and graham crackers before we put this big block on it?
That would have been a big mess.
It would have been a big mess. I suggested it to Math Dad and he was like, no, please don't. But this is what happens to rocks underneath glaciers. The weight of the glacier is so large that it pulverizes and grinds up rock as it's moving down. So when we're gonna look at some pictures of glaciers in a minute, you're going to see a lot of brown material on top. And that's because the glacier is literally carving out a valley as it moves.
Okay, so what if like a car was in front of a glacier and the glacier hit it? What would happen?
Well, if a car got underneath a glacier, the glacier went over the top of it, the car would really be turned to aluminum and steel dust. Oh, wow. The rocks that are underneath glaciers often get ground to really fine small pieces. There would not be a car remaining afterwards. Let's go look at a couple pictures of glaciers. We've got some cool images here to help you appreciate just how amazing these structures are. Glaciers are sometimes called rivers of ice. And with this picture right here, you can see it really does look a bit like a river.
It looks like it's flowing. It's got a stripe there.
These stripes come from that sediment. We were talking about how the weight of the ice will grind up rock into small pieces. So you get these stripes sometimes where near hills and the sediment just gets carried down. But this glacier is wrapping around the valley and spilling down.
How fast is that moving?
It all depends. Most glaciers are pretty slow. They're going to be about 10 inches a day-ish.
Oh, so you might not even be able to see them moving.
25 centimeters? No. Most glaciers, if you stand and look at them, you're not going to see them moving. You would have to set up a time lapse for a whole day, and in that whole day, it might move this much. That's very slow.
That is really slow.
But we'll talk a little bit more about how they move in a minute, because there are exceptions. Now, here is a map of where you find glaciers in the world. And you can find them just about on every continent, even in tropical locations. This glacier right here in the top of this really tall mountain in Indonesia is actually disappearing. It's probably going to disappear completely in the next 3 to 10 years. It's melting because of climate change. But Africa, Mount Kilimanjaro has some glaciers. The majority of them, though, are in Antarctica and in Greenland and up here in the north.
That makes sense. The poles would be a lot colder.
Yeah, but anywhere where you have mountains that are tall enough that they get snow year-round, you will have the conditions that could form a glacier.
Oh, way cool.
And depending on how the glacier ends and how it's formed, we actually have different types of glaciers. So an alpine glacier is one that is formed in the tops of the mountains, and these are glaciers in Pakistan. Pakistan actually has a lot of glaciers, more than most countries.
The Himalayan mountains.
Yes. And if the glacier ends in a mountain valley or ends on land, we call that a mountain or an alpine glacier. So you can see this glacier is flowing. You have ice that is moving down the valley, but then at the end of the glacier, you do not have an ocean. So that's a mountain glacier. If you end at the ocean, this is a tidewater glacier. And these are the types of glaciers that when pieces break off, they form icebergs.
That makes sense.
Yep, we'll learn a little bit more about those in a minute. But there's a third type of glacier that is kind of a funny one. These are rock glaciers.
Okay. I've even been to a rock glacier. I still don't know what it is.
So let me explain it, and then I'll tell kind of a funny story about our trip to a rock glacier. So rock glaciers have ice down underneath the rock, and some of them used to be really big ice glaciers, but then as the glacier, more and more of it melted and more of it got covered with rock, then all of the ice is covered with rock, and when you look at it, it doesn't look like a glacier, but it moves like a glacier.
It looks like flowing rock.
It does. And so if you're hiking on top of this, there's just going to be big pieces of rock everywhere. But over time, if you set up a time lapse and you look at this year after year, it will slowly, few inches at a time, be creeping down the mountainside. And where is the fresh rock coming from? Well, this cliff. This cliff is eroding. Pieces of it will break off and land on here. And then in the wintertime, more snow falls and some of that snow melts down and there's ice sort of holding all the rocks together.
So that took thousands and thousands of years to...
These are definitely old structures. And now a quick funny story. I heard that there was a glacier in Great Basin National Park in Nevada. And when we first moved here, and I thought that was so exciting, we had to go see it. So we drove up to the park and we hiked and hiked and hiked. And the kids kept saying, when are we going to see ice? And they were imagining like this blue glacier ice. And there were just rocks and rocks and more rocks. And finally, I met up with a geologist who explained to me the difference between a rock glacier and a regular glacier. And I said, I wish I would have known that before we took the kids on the hike, because they were very disappointed.
Tragic.
The rock glacier was cool, though. And you could actually hear like some rocks kind of falling down from the cliff way, way in the distance. And so he's like, there it is, active evidence of this glacier process happening. But again, it's moving very slowly. So the whole entire big rock glacier field, it's going to creep forward just inches in a year. It's not going to be moving very fast. However, there are glaciers that sometimes do move very fast. And one of them is the Mudrow Glacier in Alaska. So this is in Denali National Park. Like most glaciers, its usual speed is just a few inches a year. But about every 50 years, enough pressure builds up on the glacier and probably a lot of meltwater underneath that all of a sudden the glacier will surge and go forward. And when it does, it goes up to 60 feet in a day.
Whoa.
Really fast. So here's a picture. This glacier, Mudrow Glacier, just started surging a couple weeks ago. And it was in the news and quite exciting. And so if you go to Denali National Park, you can see the maps and all this data that they're doing as the glacier is surging.
So that's moving fast enough that you actually could see it happening if you want.
Yes, and there's some cool time lapses online that you can see. And once it started surging too, all of these cracks filled up. And that reminds me, let's go to the notes. I think we're on page 102. Am I right?
Yes.
102. Let's talk a little bit about the terms that you need to know to understand a glacier.
Okay, there are definitely some new terms here that I didn't know.
So Math Dad, you asked the question of what would happen if there was, let's say that you drilled down, made a big hole in the glacier, dropped a car in the middle at the very bottom, and then let it cover back up with ice and said it will come back and check in 100 years. What would happen to the car?
Be pulverized.
It would be pulverized. There is a word for the pulverizing that a glacier does when it takes rock and grinds it into tiny little bits. That word is till. Till is the fine, sandy sediment that a glacier forms. And it's different than sand that you'd find at a beach or that's formed by something else, like a sand dune. This is a coarse material, and glaciers make a lot of till. And that till can get deposited down here at the end of the glacier. Sometimes it will form big stripes or rows. So that is till.
Till.
Yep. And then the zones of the glacier are important to understand. And the word search I'll let you guys do on your own time, but let's look here at what is happening. So in our glacier, there's an accumulation zone up here where more snow is falling than is being lost by evaporation or by melting. And you're going to get more and more and more water and snow coming down. And then here in this zone, it's the opposite. You are going to be actually losing more ice than you are getting through evaporation. So this is the ablation zone.
So that zone would totally go away if it weren't being replenished by new snow pushing down?
Yes. So if you don't have a lot of new snow coming down at the top and the glacier pushing and flowing, then the ablation zone, you'll have things melting and it can start to disappear a bit. And then if you have cracks in the glacier, those are called crevasses. And sometimes you can even have lakes underneath a glacier. And then these special long things are called moraines. And if you live in, back east around Minnesota, Michigan, there are a lot of moraines that are still visible, these big deposits of till that were left over from glaciers.
What did you call the lake?
Subglacial lake.
Subglacial lake. Got it.
Some glaciers actually do have water underneath them, but they're so cold. How could they have water underneath? It has to do with all the pressure of the ice.
Oh, it causes it to melt?
Yes, all that pressure. You can have a lake, even though the lake is so cold that if all the ice were gone, it would be frozen.
So I'll just point out in the word search, there are actually several words on there that were not included on this list. So feel free to look for those as well.
Some mathy words.
Actually, I don't know if this one was math themed.
Oh, they were just fun words.
These might be more science themed.
All right.
I don't know. I can't find them all. I forgot what they all were. So you're going to have to find them because I can't tell you.
We're going to share a quick time lapse now and take you to the Columbia Glacier in Alaska. And this time lapse goes from 1995 up to 2018, I believe. And if you watch it, you can see that there's sea ice over that bay, but then the actual glaciers themselves are going further and further up. Let's play it one more time. There it goes. So back in the early part of the century, that glacier came all the way down into the bay. But now it's split into those two arms. And if you want to see the part where the glacier hits the ocean, you have to go way up into the bay.
So is the glacier going uphill now? Why is it retreating over time?
So it looks like it's going backwards, right?
Right. Yeah.
But it's not going backwards. The glacier is still flowing downward, but it is melting faster than it's being replenished.
Gotcha.
All right, let's look at one more video. There's another shot of the Columbia Glacier that we're going to look at. This is one of the fastest changing glaciers in the world. And this is from the NASA Observatory, and it's a false color image. That means that they have colored things so that it's a little bit easier to tell, like what's old ice and new ice. And the mountains look neon green. In real life, they don't look like that.
I can't make it any bigger, unfortunately.
But here again, look at that long tongue of the glacier that's coming out into that inlet, and watch how over time it shrinks back. It looks like the glacier is retreating, and it looks like the glacier is going backwards up the mountain, but the glacier is still flowing down. It's just that it's melting
earlier in the process,
faster than it's being reformed.
Gotcha. Yeah, that's it. Fun color image.
And this is an important thing to understand, that glaciers are flowing. And one of the best ways to appreciate that is by looking at time lapses. Let's go back to our images here real fast, Math Dad. The slideshow that we've got. So we were talking about the Mudrow Glacier. We showed you the Columbia Glacier from those two sites. And now let's talk just a little bit about how much glaciers have changed, because they're one of the most dramatically impacted features from the warming that we're experiencing in climate change. These photos, this was the Muir Glacier in 1941 versus 2004, a huge difference. That glacier has retreated dramatically. And then here's the South Cascade Glacier in Washington. And you can see from 1928
so lots of snow.
Yeah, to 2003, an enormous difference, but especially from 1979, that's not that long ago, to 2003, you have a glacier that came all the way down the valley to now one that is retreated very far up. But again, these glaciers are not moving backwards. They're just melting faster than they're being replenished. And one of the best ways that you can see time lapses of glaciers and look at what's happening with glaciers around the world right now is to go to, let's show this slide so that you guys can see the website. If you want to check this out later, you can. If you go to climate.nasa.gov, there is an incredible resource, and we're going to look at a couple of these right now.
NASA has some amazing stuff.
Yes.
So much of what we've showed you in this course has come straight from the NASA website.
There's an amazing part here, little slideshow here we're going to show you with a time lapse. And Neptune asks, why do we need glaciers, or why are they useful? And this is a good question. And it's really because they store fresh water for us and they regulate the temperature of our planet. So they're an important water source. And notice, can we maybe play that beginning part again real fast, Meth Dad?
Yep.
Notice how the scale of this, so that's a helicopter, and now we're zooming back.
Zooming back.
And still zooming. And I'm seeing several people ask for a link. Don't worry, we'll have a link in the description after the video is done, and you can look at it. You can look at it later, but check out how this is moving over the course of 2 years. And you can actually see it creeping over the horizon. It's like the whole entire landscape
is flowing. Yeah.
And again, remember that wall of ice that we see sometimes there, that's like 250 feet tall. It's enormous.
Wow.
And then it retreated a bit, so they kind of moved the camera back. But that is a view of one of the huge glaciers in Greenland. And Ryan says, a helicopter? I thought it was a fish, right? It looked really small, but it's enormous.
Yeah.
These glaciers in Greenland that we're going to show you, this next one too, they're tidewater glaciers. And in this next video clip we play, there is a little mistake actually. It says at the bottom, in the big text, it says that it's 1 year, but this is 2 years. And I want you to notice, so we have 2 years, that means we're going to have 2 winters. Notice what happens to the pack ice in the winter versus the summer. It's going to look really different. So here's the Store Glacier in Greenland. And again, just like that other one, super tall, 3.6 miles across.
Wow.
And that ice face right there, 250 feet tall. So we're looking at miles of glacier here. And this is what type of glacier, Math Dad? Alpine or tidewater?
Well, it's hitting the lake, or the ocean. So it's a tidewater.
It is. It's a tidewater glacier. And in the summertime, the water is pretty open. And then here we're in the winter time, and you can see it fills up with pack ice. But what direction is the glacier moving?
Downhill.
Always downhill. It's
Yep.
moving downhill. And then we have summertime again, and you can see pieces of the ice, the glacier breaking off and forming icebergs. And then we get our second winter, and still it is just steadily moving downhill into the ocean. So glaciers add a lot of fresh water into the ocean. And that's an important part of the whole thermohaline circulation system, is that input of fresh water from glaciers.
And so you say it's floating downhill, but the water level underneath should be about the same. So I guess in this case, the heavier stuff that was uphill before it got to the water is pushing it down. Yeah.
Yeah. And let's take a look real quick at our little demo we did at the beginning. So our big piece of ice, went all the way to the bottom, and the small piece of ice has moved about that far.
2 ice cube lengths.
Yep. So it is slowly moving now, especially that it's melting and it's wet at the bottom. But you can see that the amount of weight you have, that makes a big difference as to how something moves.
Yeah, absolutely.
And Anna wants to know, did they do a time lapse for a whole year? there are several locations in Greenland where they have monitoring going on all the time to track these glaciers, because right now glaciers are changing pretty dramatically. And also, we really care a lot about iceberg formations. Really big icebergs can cause problems for ships. You remember what happened to the Titanic?
It sank because it hit an iceberg.
Because it hit an iceberg. So we want to be tracking how the glaciers are moving to better understand climate change, but we also want to know about big icebergs. And this next clip we're going to show you is when in the world of icebergs, this is a small iceberg, but to us, you and me, it's going to look huge. We're going to see an iceberg come off the Store Glacier in Greenland. So for scale, if the US Capitol building was there, that's how big it would be. This is hundreds of feet tall.
Oh, I see pieces breaking off.
Yep, there are some pieces breaking off. And then...
What was the fancy name for breaking off?
Calving, like C-A-L-V, calving. And there it goes. Look how
that whole
big
thing came off.
That whole entire thing. And do you see how it turned on its side?
Yeah. Why did it turn on its side?
It turned on its side because an iceberg is always going to float in the most stable position.
Look at it go.
And there it goes, floating down. So that's a piece of the glacier that broke off, and now it's floating into the ocean.
Wait, what's happening now?
Just for fun, they're playing it backwards so that you can watch it again, because it's very awe-inspiring and satisfying just to see that awesome force. And it makes you really get an appreciation for just how much of the glacier is underwater too, when you see it start to break, and then when it flips up, it's like, whoa.
And that one wasn't sped up. That was the real time, or do you know?
I'm not. I think it was sped up just a tiny bit, not much. Now there is a really fun website where you can draw your own icebergs. I want to show you this real quick, and then we'll get to some Q&A, and we've got some poll questions for you guys. But at
let's see if I can.
Here, if we pull up the slides real quick, I've got it on the slides to show them the website. Poor math dad today, I told him, I was like, you're going to have videos, you're going to have the slideshow and the notes, and you've got to bounce back and forth between all three. So this is joshdata.me and Iceberger. Kind of a funny website, but this was just a person who happens to do research and is good at coding and website design. And someone had a tweet about how icebergs form, and he was like, oh, I'll make a little system where people can draw their own.
Okay, so check this out. I'm at this website right now. I'm going to draw me an iceberg. So my iceberg is going to look like this.
And then when you let go, it'll show you how it would really float.
That was cool. What if I did an M for Math Dad? How would that float? Or do an S for Science?
An S for Science would be cool. And then you should do one up top and let it splash into the water.
Oh. All right. I think I should do one up top with figure 8-like thing. Let's try it. Oh, it only did one loop of it.
It has to be connected.
But it did splash.
And then when it comes back up, icebergs always, their density is similar enough to water that they're going to float with about 90% in underwater and about 10% above. But if you make a long, skinny iceberg, it's not going to float long and skinny. It's going to float sideways because that's more stable.
So I've seen pictures of long, skinny icebergs. Are those just photoshopped?
Those are often just illustrations. But it all depends on what angle you're looking at. If you're looking at an iceberg that's really long, like out, from where you're looking, it might look like most of it goes down, but you don't see the part that's going out sideways.
I can sit and play with this for hours.
All right. Let's go back to our main view, and we have just a couple questions I want to answer, and then we're going to talk a little bit about sea ice, and then we have polls for you guys. So Ryan wants to know, how did I get an ice cube this big? And the answer is from the grocery store.
That they actually had
big. They have block ice, and they have like crushed ice or ice cubes that you can get. So I got that at the grocery store this morning.
When people go on vacations and they're going to need refrigeration for several days, a big block of ice like this is going to last a lot longer. It's very helpful.
And then Julia has a question about Iceland versus Greenland. And it is funny that Greenland is called Greenland when really it is so much of it is covered in ice. But that just goes back to the history of when they were first named.
Yep. I think the Vikings were trying to sell it like, oh, this is a great place to move. It's called Greenland. See,
not very much of Greenland is green, and the part that is green is only green for a tiny little short window in the summertime. Now, we talked about glaciers, which are on land, and they're carving out sediment as they go, and we talked a little bit about icebergs, but there's another type of ice that we want to mention real quick, because remember, when we talked about the water on Earth, most of the water is salty in the ocean. And then of the fresh water, water that you and I could actually drink, then most of that is ice. Glacier ice, ice in ice caps, and the ice cap at the North Pole is actually floating on water, all of it. So let's take a look at this real quick. This is a website from on the NASA website, and again, I'll have the link down in the description at the end. But this video we're going to play, we don't have audio with it, but I'm just going to sort of narrate for you. This is looking at the North Pole, and the North Pole is not static. It's not like in Antarctica where you can just plant a flag and then that flag is going to stay there. The North Pole, the ice is going to be moving around because of ocean currents. And maybe let's...
Does that move the North Pole?
The North Pole...
It's not where the flag was planted?
No, so the flag location has to be changed to stay with the actual location of the North Pole.
That's kind of funny. It's like it's taunting the scientists who planted the flag.
Yeah.
So,
So with satellite data, this is colored so that you can see that the thicker ice is white and the thinner ice is a lighter blue.
Okay.
And we're going to, let's go about halfway through. And now you can see that the ice gets replenished within the Arctic because some of the ice survives each summer and it grows older and it gets thicker. And especially in the region north of Alaska called the Beaufort Sea, that's where the ice spins. And you can see this gyre where it's going around in a clockwise direction. And oftentimes it takes several years. Gradually the ice is getting older and then getting thicker. And then it's going to come out over on the other side of Greenland.
How thick do you
About
think?
6 to 10 feet thick is the older ice.
Okay,
There's
so
a little...
not big like some of those glaciers we were seeing.
No, not hundreds of feet big, but thicker. And the thing is with climate change, we've seen less and less replenishment. So there's being more melt during the summer. And so the ice that goes out through the Fram Strait has not been compensated by the ice growth. It's not getting thicker.
So over time, there's less and less polar ice.
Yes.
Less sea ice in
Over
in
time.
the Arctic.
Over time. And we're starting to see that this area in the north of Alaska that used to be kind of a nursery for sea ice where it would grow and thicken, it's been open up instead in the summertime with open water. And that used to never happen.
And that's due to rising temperatures.
Yeah. And then this final image in this video kind of shows you before and after. And it's really remarkable to see the difference.
Oh no.
Oh, Math Dad.
I tried to jump ahead. I failed.
It's okay.
All right. We'll be patient.
And if sea ice disappears completely from the Arctic Ocean, that's going to have a dramatic impact on the Earth's climate. So this is what we're seeing from 1984. Math Dad and I were alive in 1984. That's not that long ago. And then now in 2016, there's a huge difference between the amount of sea ice that we have.
Yeah, that's interesting. So if just in our lifetime it's changed that much, and if it changes that much again in the next generation, I mean, wow, we're going to see some rapid change.
We are. And I saw a couple of real good comments in the chat. Maya says we need to slow down climate change. We absolutely do. And then a couple of people are asking, well, what would happen if all the glaciers melted? And if all the glaciers and the ice caps melted, sea level would rise more than 200 feet. And it's not possible that they would all melt all at, like within a year. It couldn't happen that fast, but we definitely do not want that to happen. The good news is that there has been some research looking at in the beginning of the Pliocene, the era that we're in now, there was a warming period where things got really warm, and then we went back into the most recent glaciation period. So we've seen that in fairly recent history, the planet has warmed, and then it's corrected and cooled again. So if we can reduce carbon dioxide levels, we should be able to have glaciers get bigger again rather than getting smaller.
I'm all for that. It turns out that the interglacial zone, so we actually like the ice ages, very friendly to most mammals.
Yes.
And the default, if there's no ice on Earth, like that's actually much hotter than
we're comfortable with.
Or maybe even able to thrive on at all. So.
One last little question about glaciers. You might have seen pictures of glacier ice where it's totally blue, but this ice is white. How does glacier ice get blue, Math Dad?
Well, the ocean water. Why is the ocean blue? No, this is good.
It's actually a similar reason. So water does a good job of reflecting all of the other wavelengths of light except for blue. And so
scattered.
It scatters the other wavelengths, but the blue light still gets through because it has a different energy than red and some of the other colors. But also there are a lot of air bubbles in this ice. And at the bottom of a glacier, especially with really old glacial ice, you don't have as many air bubbles. They get pushed out by all the pressure. And so that helps the ice turn blue.
Nice.
And now it is time to go to itempool.com/sciencemom/live. And while you're getting over there, we want to wish a very happy birthday to Annika in Seattle and a happy birthday to Colin, who turns 12 today. Happy birthday, Colin.
Happy birthday indeed. All right. Our first question is, what portion of the world's land is covered by glaciers?
Oh, Math Dad, I forgot to tell them this one.
Well, that's okay. Let's see if they can do it without you, Science Mom.
Ooh.
So we get 10%, 20%, 30%, 40%. Obviously, it's less than 100%. But
it is less than 100%.
What portion is covered by glaciers? And I'm not talking about the oceans. This is just the land mass.
Yep, just the land. What portion is covered by glaciers?
Yeah, so you've seen lots of maps of the world, but maybe glaciers were not prominently featured on those.
And a glacier is different than an ice cap. So the ice cap in the North Pole, that ice is not a glacier. I'm all nervous, Math Dad. I'm like, I forgot to tell them this. Are they going to guess it right?
They're going down, Science Mom.
We'll find out.
All right. Maybe.
If Math Dad can get his mouse to work. Come on, mouse, where are you?
Where's my mouse? I don't know. Keep working on this. I can do it, guys. I can do this. How did I lose my mouse?
I do not know how you lost your mouse. That is really bizarre. Well, I'm just going to go ahead and reveal the answer. The answer is 10%, but I have no idea if that is what everyone chose or not. Oh no, you guys, it's a technical difficulty day.
We'll never know the answer. What could I possibly try here? Oh, now I see answer switching now. They must have heard your... Oh, man.
This is really bizarre, you guys. The mouse just completely...
Clearly it was there.
It's gone. Math Dad's doing the unplug and replug. It's back. The mouse is back.
All right. But now can I get it to reconnect? That is always the tricky part.
There it is. And Science Mom member says, well played, kids.
You broke it. You broke it on purpose.
So see, Beth, that's what happens. If we ask a question that I didn't cover in class, then Item Pool and the kids conspire to be like, aha.
Some little stinker like hacked my computer like, oh yeah, Math Dad.
We'll get rid of your mouse so that then we can switch the answer.
Somehow 75 people voted for the right answer. I don't know. I don't get it.
There's a reason we call them the unbeatable science kids.
All right. If all the land ice melted, sea level would rise by how much? So 15 feet, 50 feet, 100 feet, 200 feet?
And I did see some comments in the chat where someone was like, the world's going to end. And I have to say with climate change, there's still time for us to act and change things. And sea level rise could not happen all at once. It's something that would take a couple hundred years to happen, but still, we don't.
And most likely thousands. But we'd like to be around a lot longer. We'd like to preserve things.
We want to keep Florida on the map, not underwater, right?
That's right.
Yes.
All right, and 200 feet is correct.
They knocked this one out of the park. Good job, you guys.
Did you tell them that?
Oh yeah.
Okay, I didn't remember that.
You weren't listening.
I wasn't listening. I was too busy switching screens here. All right, true or false? Glaciers exist on every continent.
We saw a map at the beginning.
I don't think they're going to remember, though, because I don't think we specifically mentioned this fact.
I think I did.
This is it.
I don't think it's at Math Dad. I think they're going to get this.
Let me start stretching so I ready for a victory dance.
We have a clear favorite, so I'm going to go ahead and finish and reveal, even though not quite everyone has voted yet. And they say false, and they are correct because there are no glaciers on Australia.
They said true, Science
Oh,
Mom.
no, they said true.
Mwahaha!
All right, do your quick little victory dance, Math Dad.
Oh, 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 staying alive, staying alive.
Now, Australia is the only continent without glaciers, which is kind of surprising when you think about it, because Africa has
I
glaciers.
thought Africa wouldn't have glaciers, but
South America, there are several tropical locations that have glaciers. But yeah, this one was a little sneaky because we went through that map kind of fast.
All right. A well-preserved woolly mammoth was once found under a glacier. Is that true or false? So
you probably...
This one was only discussed very indirectly today.
It was, but we did kind of talk about what happens at the bottom of a glacier. But I bet some of them have seen pictures of like frozen woolly mammoth remains, because there have been some.
No hints, Science Mom. No hints.
That wasn't a hint.
No.
Nope, that wasn't a hint. All right, we're gonna finish and reveal it. They say false, and they said true. Uh-oh.
Aha. The correct answer, is that it's false. So why could we not have a well-preserved woolly mammoth under a glacier?
Because it would be pulverized. It would be ground to bits by all the weight of the glacier. That's why.
That's right. We talked about if a car was under a glacier, it would be mushed up. And we even had a name for all that sediment that's left once the glacier goes over. It was till.
So woolly mammoth, if it was under a glacier, would be turned into till. It would be all ground up by the weight. You'd have thousands and thousands of pounds of ice on top.
So not a well-preserved one.
Woolly mammoths have been found in permafrost, in areas where you have ice that is not moving. Because you do have snow accumulation that makes thick layers of ice where it's always frozen. And if it's flat and it's not moving, then it's not a glacier. All right, next one.
All right, our last question. Which of the following statements is false? So we've got a glacier is ice that moves under its own weight. Most glaciers move quickly, advancing 50 feet or more per day. Glaciers can be hundreds of miles long. Or a tidewater glacier is a glacier that ends at the ocean.
Ooh, they're going to smash this one, Math Dad. I know it.
I don't know. This could be the time when I come out on top, because it's 2-2, Science Mom. 2-2.
Surprisingly, yes. Although I think it was kind of like a little extra sneaky questions in there. And Item Pool got mad at us because one of the questions we hadn't covered.
It did get mad at. Or there's a hacker. I'm still not sure which of the two it is. But all right. Let us reveal the answer. Most glaciers move quickly, advancing 50 feet or more per day. Okay, that is not a true statement. The glaciers are going to move more slowly than that typically, and only at rare times will you see it advancing as much as 50 feet in a day.
Very rare. In fact, we
call it surging, right?
Yes. The Muldrow Glacier that's surging in Alaska right now, it only does that once about every 50 years. And less than 1% of glaciers surge. Only glaciers that are on really steep slopes have that ability to move that fast. And they're only going to do it for a short period of time, and then they slow back down. A couple of really good questions that came in from our moderators. So Chowie Combo wants to know what happens if all the glaciers disappeared for a day, like if just suddenly they were gone and then they came back. There would actually be some movement of the land if that happened, because especially in Greenland, the weight of the glaciers is heavy enough. It's actually pushing down on the land a little bit, and the land mass is a little bit lower. The second thing that would be a really big issue, if you suddenly like snapped your fingers, glaciers were gone, snapped your fingers, glaciers came back, is that a lot of glaciers actually act kind of like dams keeping the ocean from going inland. There are areas of Antarctica that are below sea level but are filled with frozen ice. And if the glaciers disappeared, the ocean would pour in, and it would change the way that would change everything around Antarctica.
Yeah. Okay, that was an interesting question.
Yeah. And then Diamond.
I'm glad you knew the answer, because I was going to say the wrong thing.
And then Evie has a great question. Has Earth always had ice on it? Have we always had glaciers? And the answer is no. Back in the Cretaceous, Earth was not in an ice age. We're in an ice age now, although we're in between.
The interglacial period.
Yes. Back in the Cretaceous, when the dinosaurs roamed the Earth, sea level was much, much higher, and there was no ice, really. There were no ice caps. If there were glaciers, they were very, very rare and maybe only a little tiny bit on the tallest of the tallest mountains, but not like we have now. So good question.
Somebody pointed out that New Zealand had glaciers. So does that count as Australia? I didn't think so. But
yeah, no, they're not not the same continent.
If you had to lump it in as a continent, though, I would if you had to say New Zealand is on a continent, what continent is it? I don't know what the tectonic plates are, or
Australia is on its own continent.
It's its own plate.
Yeah, that's a good connection though, because New Zealand does have glaciers. And then Amaya asks, what's the difference between dirty ice glaciers and clean ice glaciers? I am not sure. I've not heard that term before, but I do know that the glacier, the Muldrow Glacier in Alaska, often it has a lot of sediment on it, but as it surges, it's cracked and it looks totally different. So depending on what type of rock the glacier is going through, some glaciers pick up tons of sediment, others not quite as much. And sometimes when you look at glaciers, they almost look brown because of all the sediment they have in. So my guess would be that dirty ice would just be more sediment, more till that's mixed in with the glacier. All right.
Yeah, I had no idea that glaciers were moving on such a scale. To watch some of the videos where they were flowing, really kind of eye-opening.
It's amazing, isn't it? I really love glaciers, and I hope, I've never seen one in person. I hope someday I'm able to travel and see one because they just look incredible. But if you do go visit a glacier, you've got to be careful of the crevasses, those cracks up top. And then would you want to be in front of a glacier that could surge?
No.
No. Or make sure that it's been well studied by scientists so that you don't happen to be in front when it starts moving fast all of a sudden. Thanks for joining us, you guys. And we will see you on Friday with a lesson all about maps and navigation.
Work hard, grow smart, and we'll see you next time.